Hey everyone, and welcome to this explainer. Today, we're zooming in on 2025. This was, without a doubt, the watershed year where theoretical science finally packed its bags, left the laboratory, and jumped straight into our daily lives. I am absolutely pumped to walk you through this because we're looking at a profound shift. We're no longer just staring at abstract theories on a whiteboard. We're talking about real, tangible tools that are actively putting in the work, reshaping medicine, transforming computing, and totally rewiring our global economy. So, you know that old question, what happens when science fiction becomes science fact? For decades, stuff like quantum computing or gene editing, it all kind of lived in this speculative, maybe someday bubble. But in 2025, that narrative just completely flipped. We've officially moved way past asking if a technology works. Now, the only question that matters is, how fast can we put it to work in the real world? Google's 2025 Year in Review actually captured this paradigm shift perfectly. They pointed out that AI is shifting from being just a tool to becoming a true utility. It went from something people might occasionally tinker with to something they actively put to work alongside them. But here's the crazy part. This isn't just an AI story. This exact same shift is happening across quantum physics, biotech, robotics, you name it. It's the absolute defining theme right now, the tangible applied uses of these massive scientific breakthroughs. All right, so here is our quick roadmap for today. First, computing leaves the lab. Second, CRISPR and medical marvels. Third, FDA adapts to new tech. And finally, number 4, the economics of innovation. Okay, let's dive right into section 1, computing leaves the lab. So, for the longest time, the giant roadblock for making quantum computing practical was error correction. Quantum states are just incredibly fragile. But early in 2025, AWS and Caltech totally shattered that barrier. They built this new Ocelot chip, which actually reduces quantum errors by up to 90%. And get this, they did it using something called cat qubits, which, sadly doesn't mean there are tiny felines running around inside your computer. It's just the name for a highly stable quantum state. But jokes aside, this was a massive milestone. It proved that scalable, error-corrected hardware is not just a pipe dream anymore. It is completely possible. And to fully grasp the sheer mind-bending scale of what this new hardware can do, check this out. Google rolled out their 105-qubit Willow chip and showed off what scientists call true quantum advantage. They ran this incredibly complex molecular calculation, and Willow knocked it out in just 5 minutes. If you tried to run that exact same math on the absolute most powerful classical supercomputer on Earth, it would take 10 to the 25th power years. That is literally longer than the universe has existed. Wild, right? But remember our main theme today, applied uses. Was all that computing power just a flashy parlor trick? Absolutely not. IonQ and ANSYS took a 36-qubit system and applied that raw power to simulate medical devices. And guess what? The quantum machine actually outperformed classical high-performance computing by 12% in a real-world commercial task. This is the inflection point, folks. Quantum computing has officially entered the chat for everyday commercial use. Moving right along to section 2, CRISPR and medical marvels. I want you to take a quick second and think about how small 3.5 millimeters really is. It's roughly the width of, maybe 2 grains of sand. Well, in 2025, Northwestern University developed the world's smallest, fully biodegradable pacemaker, and it measures exactly 3.5 millimeters long. It is so ridiculously tiny that doctors can just non-invasively inject it straight into the body with a syringe, let it do its job for a bit, and then it just completely dissolves on its own. Talk about applied engineering. We're shrinking life-saving hardware down to the microscopic level. Meanwhile, down at the genetic level, CRISPR made a huge jump from the research lab right into everyday clinics. Take Casgevy, for example, an FDA-approved gene-editing medicine. By making a precise edit that essentially disables the genetic switch keeping fetal hemoglobin turned off, this therapy restored functional oxygen transport in sickle cell patients. And the real-world results? Just stunning. Out of 17 trial patients, 16 became completely free of painful vaso-occlusive crises. We are literally snipping disease right out of the human genome. And the application certainly didn't stop there. You see, initially, folks thought CRISPR was only going to be good for monogenic inherited disorders, diseases caused by just one single faulty gene. But in 2025, the applied uses of CRISPR just exploded. We saw major breakthroughs targeting a hugely diverse mix of conditions. We're talking infectious diseases like hepatitis B, in vivo treatments for high cholesterol, blindness, and even reversing chemotherapy resistance in lung tumors. The recipe book for precision medicine just blew wide open. All right, let's look at Section 3. FDA adapts to new tech. So, with all this rapid innovation, we ran into a major structural bottleneck. For decades, the gold standard for getting any drug approved has been the randomized controlled trial. Usually, you need hundreds or even thousands of patients to prove a drug actually works. But what happens when you create an ultra-targeted genetic therapy for a rare disease that maybe only affects, say, 20 people in the entire country? Running a traditional trial isn't just hard, it's mathematically impossible. You literally just don't have enough patients. To solve this, the FDA did something incredibly pragmatic. They introduced the plausible mechanism framework. Basically, this replaces those impossible bureaucratic hurdles with a super digestible, 5-step logical process. So instead of demanding a massive, impossible trial, the FDA now lets drug makers prove a therapy works based on its underlying mechanics. First, identify the genetic abnormality. Second, target the alteration. Third, use the natural history of the disease as a baseline. Fourth, confirm the target was actually edited. And finally, show clinical improvement. It's just a brilliant masterclass in how government institutions can pivot and clear the runway for applied science. And that brings us to our final section, number 4, the economics of innovation. This ties into such a fascinating concept, which actually won the 2025 Nobel Prize in Economic Sciences. It was awarded to Philippe Aghion for his theory on sustained growth through creative destruction. If you haven't heard the term, creative destruction is basically the dismantling of long-standing practices or paradigms to make way for new innovation. And honestly, it is the perfect conceptual anchor for everything we've talked about today. The old ways, classical computing, bulky traditional pacemakers, outdated FDA trial structures, they're all being rapidly dismantled right before our eyes to build a much more efficient and capable world. Just consider the breathtaking timeline of commercial milestones we saw in just the final 2 months of 2025 alone. In November, we got that major CRISPR breakthrough for lung cancer, plus Google launched Gemini 3, embedding highly advanced AI directly into our daily search habits. Then in December, researchers unveiled the world's smallest programmable robots. This right here, this is what creative destruction looks like in real time. It's a compounding, relentless acceleration of innovation. So, as we wrap up this explainer, I want to leave you with one absolutely vital question to chew on. We've clearly seen how forcefully science leaped from the lab into our daily lives in 2025. But are our institutions, our economies, and our everyday societal rules truly prepared for a world where these massive breakthroughs are being applied faster than we can even comprehend them? We are literally living in the future today. Thanks so much for joining me on this one. Keep questioning, keep learning, and I'll catch you in the next explainer.